Okay, thank you, Shirley. Can you hear me okay?
Yes, we can.
Good. So I'd first like to congratulate Shirley and Mike on getting this MERSEC award and for setting up the Institute. I think you all recognize Shirley's car there, a nice clean car. What I would like to do is just give you a little bit of history about why materials are so important. So, as you heard a little bit a few minutes ago, much of the most exciting research is at the interface of disciplines, and materials is a particularly glowing example of interdisciplinarity. Science knows no boundaries. There are no really disciplines in science, even though academics like putting no boundaries with departments, colleges, and schools. If you go to industry like Exxon and when Bell Labs was there, everybody works in interdisciplinary teams. There's no chemistry team and physics teams. Similarly, there are no national boundaries. Science is totally international. And really for the younger folks there, the whole world is open to you if you're a scientist. You can go anywhere, travel anywhere, essentially work anywhere. And if you look at many of the scientific breakthroughs in the last decade or so, almost all of them are interdisciplinary. So lithium-ion battery is a perfect example. I was a chemist, John was a physicist, and Akira was an engineer. And I'll give an example of our EFRC, which Shirley and Xuping are part of, as an example of another materials-centric center where a lot of different people work together. And our center, there's probably as many nationalities as there are teams. If we can go to the next slide, please. So going back a little bit in history, 1968. That was the year I moved from Oxford to Stanford. At Oxford at that point, metallurgy was part of the inorganic chemistry lab. There was no materials department. William Hume Rotherham was professor of metallurgy, so he was in the chemistry department. Crystallography was part of the inorganic chemistry lab. And probably most importantly, solid state chemistry was a key part of inorganic chemistry. And this was made very clear by J.S. Anderson, who was a solid state chemist. He was head for 12 years. And then when he retired, they selected John Goodenough because they wanted another solids man. And John is a solid state physicist. So you see how open the university was willing to be to keep solids there. And solid state being in chemistry departments was quite common in Britain, Germany, and France in particular. Now, switching from England to California, at Stanford, there was no solids research in the chemistry department. There was no solids research in the physics department. Those departments considered themselves very pure, and solids were dirty things. So solid state physics, in fact, resided in applied physics in the engineering school. And people like Ted Jabor, working on superconductivity, was in applied physics. And he worked very closely with Bernd Matthias, who was in the physics department in San Diego. But what Stanford had at that time was a new material science and engineering department. And in 1961, they started a Center for Materials Research, obtained funding to build a McCullough building, and that was one of the original interdisciplinary labs. If we go to the next slide. So let me describe my own experience. I took a chemistry BA degree at Oxford. I had Hume Rotherham for my metallurgy lectures. And Peter Dickens was my tutor and advisor for both my bachelor's degree and doctorate. And in the bachelor's degree at Oxford in chemistry, it's a 4-year degree. Your 4th year is full-time research. And my research was funded by United States Air Force Office of Scientific Research based in the US Embassy in London. And I was looking at recombination of oxygen atoms on potential nose cone materials. And I'll get back to why that's important in a minute. I then moved to Stanford University and I joined Bob Huggins's group, which was on material science and engineering, and he ran the Center for Materials Research. So as a solid state chemist, one had to join a materials activity in the US. So I came in January and I started ionic motion in solids, which is an exciting period because the Ford Motor Company had just discovered beta alumina, where the ions moved as fast as in liquids. About 2 months after I went to Stanford, Bob Huggins went to the Pentagon in Washington to lead the entire Department of Defense materials programs that included the IDLs. And he was there for 2 years, and I basically took over his group for that 2-year period. A super opportunity, which fortunately I could take advantage of. So what we did was, in fact, measure the ionic conductivity of these beta alumina materials. And because the ions move so fast, the electrodes had to be mixed conductors. So they had to have ions moving in them and electrons. That really got the whole idea of mixed conductors going and got us working really at the first steps of lithium-ion batteries. And for that, I got the Electrochemical Society Young Author Award in 1971. And for a youngster my age, not having been to Texas where the award was given, it was a black tie dinner. And Norman Hackerman was president of the society. He had a lot of clout. So for the banquet reception, he brought in the Texas Rangers on their horses to ride around the outside of the pool. So exciting times. Let's move on to the next slide. So a date that all you materials folks should bless and remember is October the 4th, 1957. That's when the space race began. That's when the Russians sent up the Sputnik and the US government decided they had to catch up and pass them. So 3 years later, the Department of Defense, ARPA, formed the interdisciplinary labs, the IDLs. There were 3 initially in 1960. So these labs were formed the same year as your campus was born. 12 years later, it was decided that no, there's a lot of fundamental research and maybe DOD wasn't the right place. So these labs moved to NSF and became the Materials Research Labs, the MRLs. And then in 1994, the MRLs became MERSECs. And I want to congratulate you all on getting a MERSEC this year in 2020. So this is 60 years since the first materials labs were formed. I want to just show you a few of the successes of materials. If we can go to the next slide. What I want to show you here is a result of our interdisciplinary work. I said this was from our NEXIS, the Northeast Center for Chemical Energy Storage, which your campus was part of, both Shirley and Professor Ong. So he was the theorist, Shirley was the experimentalist. And one of the things we were doing was trying to understand why certain materials were very good at being battery electrodes and understand all the reactions involved in that. One thing we did in the first 5 years was understand why lithium iron phosphate was a very high rate material, even though it was an electronic insulator. But this material was low energy density. So we decided in our second 4-year period to actually see whether we could put 2 lithium ions into a material without destroying that material. So intercalate 2 lithium ions into the structure. And clearly I wouldn't be talking about this unless we were succeeding. So we looked at this lithium vanadium phosphate. After many, many years of trying to make it, we succeeded. We published the results, I think, in late 2018, and we're fortunate to get the one mention of a EFRC in the President's Science and Technology highlights. And the Undersecretary for Energy came to the EFRC meeting in DC and gave two of our students what they call the 10 at 10 award. So that was in July 2019. One of those students was in my group, and the other student represented there was in Claire Gray's group from Cambridge. But there were students from San Diego, Berkeley, a number of the other campuses also involved. So this is one of the interdisciplinary activities that materials can spin off. Let's go to the next slide. And if you look at, depending on how you want to define materials, materials research has won many Nobel Prizes. You know, graphene, the fullerenes, conductive polymers, emitting diodes, the blue ones, lithium-ion battery. And then you can take maybe half a dozen techniques, which are all techniques for studying materials, including cryogenic TEM. But three messages we gave, and this was John, Akira, and myself at the banquet, to emphasize that science is interdisciplinary, science is international, and in particular, we owe the next generation, our children and grandchildren. So we do science, not for the money normally, but because we enjoy doing it. But we owe the next generation. We've had our enjoyment. Now we have to do our duty and really help solve some of the world's problems. If we go to the next slide, please. So we can solve some of the world's problems, including climate change, and materials can really help humanity. So I've just shown you a few examples here. If you look at all the challenges facing humanity, it's energy, water, food, and health, and they're all interrelated. You can't solve one without solving the others. So now is the time for green energy. And whether it's solar, wind, hydro, they need combined with some sort of storage. And clearly I'm a little biased towards batteries. And over here you see this is a 30 megawatt hour lithium-ion battery in West Virginia. This pales compared with the, I think, 240 megawatt hour system in San Diego these days. And I'm very happy to say, no, California and New York are taking the lead, both on green vehicles, on green electricity, and because we need the political will to make these things happen. They won't happen by themselves. And I'll show you a few examples of electric vehicles here. Here are two vehicles that the British ambassador took to Stockholm. Britain is very much behind EVs and are in fact banning IC engines in the not too distant future. So this is the Jaguar, this is a London taxi. This is a two-seater car that my wife and I rented in Bermuda a year ago. And here are two trucks, a garbage truck and a 16-wheeler, which are all electric, being built and tested in Washington State. If you look at the situation with water, we're going to have to do desalinization, and we're going to have to reuse the water, not throw it away. And I put this example of the astronauts on the space shuttle. We in fact talked to them from Stockholm because they were at that time just installed lithium-ion batteries in the place of nickel metal hydride batteries. Lithium-ion batteries are half the weight, half the volume, and we're going to last twice as long. But essentially everything on the space station is reused. The technology is there, we just have to make it practical for use on Earth. And a big area of interest these days is green hydrogen production. If we want to have trucks going long distances, Probably the only realistic way is to use hydrogen produced in a green manner plus storage. And I think you folks are working on health, and clearly in that area, the biomaterials and sensors are two key areas amongst others. And MERSEX and your IMDD are the ideal approach to research. We get all the different disciplines working together, we get students moving between the groups, learning the different languages between chemistry, physics, engineering, and medicine, and gives them great opportunities in the future. Let me just move to my last slide. And I just want to give advice to the next generation of scientists, particularly those in beautiful La Jolla. Now, don't stay in your lab all the time. Now, enjoy yourself. Enjoy the excitement of experiments and theory when they work. There's plenty of challenges when they don't work. And there's really a lot of excitement at solving challenges. And don't do it for the money. You're not going to necessarily get rich doing science, but it's a really exciting area. And you need to take risks. If there's nothing ventured, there's going to be nothing gained. So be willing to take risks. You're going to make some mistakes, but in the end, that doesn't matter. What you really need are smart ideas. Don't go down the old track. Do something different. Think out of the box. And finally, remember Einstein. Remember, he said, imagination is more important than knowledge. Knowledge is limited. Imagination encircles the world. This couldn't be even more true than today. You've got all your computers, you've got your Google, you can look up the knowledge, but use the imagination. So I'll stop there. Thank you very much.